Hello gems, welcome back to another video. In this video we will be discussing all the derivations from the chapter of electrostatic potential and capacitance. This is especially useful for your board exams. In the previous video we discussed all the key concepts from this chapter in just 1 hour. If you are interested in checking that out, the links will be available in the description box of this video. So with that being said, let's begin with this one. I'm gonna say all the words inside my head. We are going to derive an expression for potential energy. So here we have a system. Capital Q is the source charge. Small q naught is the test charge. We know this terminologies from the previous class. We are going to move this test charge from A to B, okay, from point A to point B. Now it is currently sitting at a distance of r. You can see that the force on this charge, on this test charge, is F, right? It is, you can obtain it using Coulomb's law. Okay, so let's find the expression for potential energy, and that will lead us to electrostatic potential, which is the gist of this chapter. Okay, so first of all we can use the logic of work. Okay, since work for a conservative system will be negative change in potential energy, so we can go from work to potential energy. Okay, so we'll consider the work done in moving this charge from A to B. Okay, moving the charge from A to B, it will be basically F dot dr, right? And we are taking it from A to B, right? A to B, or we can say this distance is RA and this distance is RB. So we are taking it from RA to RB. Okay, now you can see that force and displacement, we are displacing it along this line. So force and displacement is along the same direction. So F dot dr, basically FD cos 0, right? Direction is the same. So FD cos 0, that will be simply FD, right? So RA to RB, you can remove the vector sign, FDR. Okay, so now this force can be given by Coulomb's law. This is nothing but the electrostatic force, you can see. So we can write this force as 1 upon 4 pi epsilon naught q naught by r square, right? The current distance r square, and we are moving it by a small distance dr. Okay, we are calculating the work in moving it by a distance dr, then we are integrating that dr so that we get the total work. Okay, so that is what we are doing here. So work done from A to B will be nothing but this 1 upon 4 pi epsilon naught is constant, and Q, source charge, both the charges are also constant in this journey. Only the varying thing is this r, right? This distance is varying. Okay, so it is 1 by integration of 1 by r square, Ra to Rb, okay, and dr of course. So 1 by r square, the integration is minus 1 upon r, right? You can use the r to the power n formula. Okay, n plus 1, so r to the power 2 plus 1 minus 2 plus 1 minus 1, so that is 1 by r, and also the minus sign. So you get this as r n plus 1 upon n plus 1, right? So you can use that formula, or you can see that the differentiation of 1 by r is minus 1 by r square. So 1 by r square integration minus 1 by r. Okay, so this is minus 1 by r. Okay, so this will go from Ra to Rb. We can substitute the limits q naught, 4 pi epsilon naught. So we have minus 1 upon Ra, Rb minus this upper limit minus the lower limit, which is substitute Ra now. So this is Ra. Okay, so finally we get the work done as this. Okay, so this minus and minus will become plus, so we get Ra minus Rb, right? So this is work done from A to B. Now for a conservative system, we know that the potential energy, the work done from A to B will be the negative change in the potential energy. Okay, negative delta U we can say. Okay, or what is change in potential energy? Basically final potential energy, final potential, this is the final position, right? Final minus initial potential energy. Okay, so we can basically change signs, okay, of work, and we can obtain potential energy. Okay, we can also say like this, right? Okay, so basically your work will be, negative of work will be change in potential energy. Changes final minus initial. Okay, so final minus initial potential energy is negative of work. So negative of work, you can just flip around the two terms. Okay, q naught, 1 upon 4 pi epsilon naught, and we have Rb minus R. Okay, so this is your expression of change in potential energy. Okay, we can choose a random point in space, let us suppose at infinity. That point we can choose that the potential energy is 0. Okay, so we'll choose the point A, okay, as at infinity. Okay, this is how we can find potential energy at a specific point. Okay, so we'll choose point A at infinity. In that case, potential energy at infinity is conveniently chosen to be 0. Okay, so in that case, the simple expression for potential energy at a particular point, point B, will obtain it as 1 upon 4 pi epsilon naught q naught. Okay, and this point RA is at infinity, so 1 upon infinity 0, you get just 1 upon R. Okay, you can use the subscript B for a specific point. Okay, this is potential energy at a particular point. Okay, so this is how you obtain an expression for potential energy. Let's move to the next derivation. Discuss about potential at a particular point. So far we have discussed and found the expression for potential energy at a specific point. Okay, so now we'll be using that expression to find potential at a particular point, electrostatic potential, okay, which is the hero of today's story. Okay, so we know from the definition of electrostatic potential, potential at a particular point, that the potential at a particular point P will be given as the work done in bringing the charge from infinity to point P divided by the test charge, right? This is the test charge Q naught, which is brought from infinity to point P. Okay, so this term will give you the potential at point P. Now we also know that for conservative system, we have work done from infinity to point P will be nothing but the potential energy, right? We just saw it. This is change in potential energy. Basically, the negative of this will be change in potential energy, okay, delta U, and we choose the initial point at infinity. Okay, so initially the potential energy is 0. Okay, so basically this corresponds to your potential energy. Okay, so Vp, this is nothing but potential energy by Q naught. Okay, and this is that simple. Okay, you just have to substitute the value of potential energy, which is 1 upon 4 pi epsilon naught q naught by r, right? And you also have 1 upon Q naught, right? So 1 upon Q naught. This Q naught and Q naught will get cancelled. Okay, the potential is only due to the source charge, right? It does not depend on the test charge. Okay, so 1 upon 4 pi epsilon naught Q by R, or you can say KQ by R. So this is the potential at a particular point P, which is at a distance of small r from the source charge Q. Okay, so this is the expression for potential at point P. Okay, so let's move to the next derivation. I have an expression for potential due to a point charge. Actually, it's the same derivation as the previous one, but the previous one is using potential energy. Here we will not be using the definition of potential energy, and this is a more standard way of doing it. If you are asked for your board exams, this is the way you should do it. Okay, that was just for understanding purposes. So we derived it from potential energy, and here we can also derive it in more standard ways, okay, by using the relation between your potential and electric field, okay, which is V is equal to minus E dot dr. Okay, this is something that we discussed in the concepts lecture. This is the relation between your potential energy and electric field. You will also see the other way around, okay, few derivations ahead. Okay, so let us find the potential energy at P. Okay, so of course the integration is from infinity to point P. Okay, the potential due to the charge moved from work done basically is from infinity to point P. Okay, the charge is brought from infinity to point P. Now we know by the definition of electric field, we have found the electric field due to a point charge, which is given as 1 upon 4 pi epsilon naught q by r square, right, at a distance r from the charge q. This is the expression kq by r square. Okay, of course dr. Okay, so now this is constant, 1 upon 4 pi epsilon naught. Q is also constant, source charge, and infinity to point P, which is at a distance r, I can say directly. Okay, 1 upon r square dr. We know that the integration of that is 1 upon r square is minus 1 upon r, so I can change this sign directly. This is 1 upon r, and it is from infinity to point r. Okay, so now this will give us q upon 4 pi epsilon naught. Substitute the limits. The upper limit is r, basically at a distance r, and minus 1 upon substitute infinity. 1 upon infinity is basically 0. So 1 upon 4 pi epsilon naught, and say 1 upon 4 pi epsilon naught q by r. Okay, or you can say that the potential at point P, which is at a distance r, is given as kq by r. Basically the same expression that we obtained before, right? But this is the more standard way of doing it. If you remember the expression for electric field, basically it's over here only, kq by r square. For potential it is kq by r. Okay, not capital R, so sorry, it's smaller, same distance. Okay, distance of point P from this source charge q. Okay, so that's the standard way of finding potential at a particular point. Let's move to the next derivation. Potential due to dipole at axial and equatorial point. This is something that we did for electric field too, but here you will see some differences. Okay, so here we have a dipole. Dipole is basically two equal and opposite charges plus q minus q separated by a fixed distance. Okay, the distance is 2a over here. You can see the two charges. O is the center of the dipole. The distance is, this distance r is always measured from the center of dipole. Okay, I have always stressed on this point in the previous classes too. Okay, so this point P is at a distance r from the dipole, meaning r from the center of the dipole. Okay, now you can see that this point charge plus q is at a distance of r minus a. Okay, this is 2a, this is center of the dipole, so this is a and this is a. Okay, so the point plus q is at a distance of r minus a. Okay, r minus a, this is r minus a. Okay, and similarly point minus q is at a distance of r plus a, right? R plus a. Okay, so this distance from point P and minus q is r plus a. Okay, so here the work is simple. We are supposed to find the potential due to plus q. We already know the potential due to a point charge. We also have to find the potential due to minus q and add them with the signs. Okay, and what is the potential due to plus q, or what is its direction? Outward direction, right? Because it is positive charge. No, because potential is a scalar. Please remember that, and potential does not have any direction. That's why we just consider their magnitude and just add them with the sign. Okay, we don't have to consider the directions like in the case of electric field. Here potential is a scalar, so we just add it with the sign. Okay, so potential at this axial point P will be given as potential due to the plus charge q plus potential due to the minus charge q. Okay, so now potential due to plus q will be 1 upon 4 pi epsilon naught q by distance between point P and plus q, which is r minus a. Similarly, the potential due to minus q will be given as 1 upon 4 pi epsilon naught, the charge with the sign. Okay, charge with the sign. Since potential is a scalar, you have to be very careful about the sign. Okay, in electric field you may not be. You can just check the direction and assign accordingly, right, and add accordingly how the vector law suggests. But here you have to place everything with the sign. Okay, so now minus q, the distance between minus q and p is r plus a, right? So now we can take common. We can take common 1 upon 4 pi epsilon naught. Q can also be taken common. So here we will have 1 upon r minus a, and this minus sign will remain. So minus 1 upon r plus a. Okay, so now let's solve it further. We'll have 1 upon 4 pi epsilon naught. This will get multiplied, r minus a, r plus a. This will be r plus a minus r minus plus a, right? This is r minus a, and minus of that will be minus r, minus into minus plus a. Okay, so this r will get cancelled, and what do we have with us? Here there is a q. Okay, so I might do that here because for the equatorial one we won't need much of a space. Okay, so here we'll be getting the potential at axial point is q upon 4 pi epsilon naught. This is 2a, right? A plus a is 2a upon this is a plus b, a minus b, so that is a square minus b square, or r square minus a square. So usually for a dipole this distance is very small, okay, two charges equal and opposite separated by a very small distance, okay. So this r will be usually greater, much greater than a, so you can neglect that a basically. So you'll have the relation q upon 4 pi epsilon naught into 2a by r square. You can write this 4 pi epsilon naught as k, and this q into 2a, what is that? If you remember, charge into distance of separation is nothing but the dipole moment, okay. Dipole moment denoted by p, this is the magnitude because potential is scalar, and kp by r square, okay. So that is the expression for your potential at a axial point due to a dipole, kp by r square, or you can remember this, okay. So now let's come to the equatorial point. Equatorial point meaning any point on the perpendicular bisector of this dipole, okay. So this line is perpendicularly bisecting your dipole, so it's passing through the center of course, and here this is point P. We are supposed to find the potential at that point P, okay. So this potential at point P, equatorial point, again you have to do the same work, plus q and minus q, the potential due to two charges, and just add them with the sign, okay. So due to plus q, what is it? It is 1 upon 4 pi epsilon naught plus q divided by the distance of separation, okay. This is the distance, okay. This is distance, the distance r is always measured from the center, okay, but here the distance between q and p is the distance of separation between them, right. Here the distance was r minus x. Similarly here distance, what is this distance? This is, you can use the Pythagoras theorem, it will be under root of r square plus a square, right. You can use Pythagoras theorem, this is 90 degree, so this square plus this square and their sum and under root, okay. So here you will have r square plus a square. Now you can see where this is going, so this is plus 1 upon 4 pi epsilon naught, and this is due to minus q, so minus q, I can directly write it this way, okay. And you can see what is this distance, actually it's the same, right, because this distance is also a, this is r, so this will be under root r square plus a square. So the point at the equatorial, on the equatorial axis is at the same distance from plus q and minus q, which means that these two potentials are cancelling out each other. You can see they are term by term very same, right, and there is a minus sign between them, so which means potential at an equatorial point due to a dipole is 0, okay. This is the major difference that you can see. Other difference as comparing to electric field, okay, other difference is it is inversely proportional to r square. There we had r cube, right. So at the equatorial point it is 0, at axial point it is kp by r square, or you can remember it that way, okay. So that's about the potential energy due to a dipole at equatorial and axial point. So let's move to the next one now. I have an expression for potential energy due to a dipole which is placed in a uniform electric field, okay. So first of all, we know that in a uniform electric field, the dipole, if it's not parallel to the field, it will experience some torque, right. So suppose if you want to displace this dipole by applying some external force, okay, so the work done basically will be the work done to rotate it by an angle d theta will be the torque times d theta, right. Whatever torque you are going to apply, and for the small displacement d theta, this much amount of work will be done, okay, and this work will be stored in the form of potential energy. So that is how we are going to derive the expression of potential energy, okay. Now torque, we have seen the relation in the previous class in the derivations of your first chapter, that torque, the relation is P E sin theta, right, P cross E or P E sin theta and this d theta, okay. Now this torque is restorative. If you see the torque that is due to the electric field, it will be restorative, okay. It will be against the torque that you apply externally to rotate that dipole by angle d theta, okay. So we'll use a negative sign over here, and we know that potential energy is nothing but the change in potential energy is the work done, okay, the negative work done, or the work done is basically the negative change in the potential energy, or you can write it this way. So basically your potential energy will be the change in potential energy, small change for d theta displacement will be P E sin theta d theta. Okay, now we can integrate this and find the change in potential energy if you change the angle from theta 1 to theta 2, let's suppose. Okay, so if you are going from theta 1 angle to theta 2, what will be the change in potential energy? Okay, so similarly theta 1 to theta 2, P E sin theta d theta. Right, now we know that P is constant, E is the uniform electric field, P is the dipole moment, Q into 2E, which is constant. Okay, and this is potential energy, du integration is u, so u at theta upper limit minus lower limit, so u at theta 2 minus u at theta 1. Okay, and this will be integration of theta 1 to theta 2 sin theta d theta, right? So this is potential energy at theta 2 minus potential energy at theta 1 is equal to sin theta integration is minus cos theta. So this is minus P E cos theta, and the integration limits will be from theta 1 to theta 2, right? So we can write this as P E. We can actually take this minus sign in and flip the limits, right? So that is one of the properties of your integral, that we can use the minus sign to flip the limits. So we can take this as upper limit, so it will become cos theta 1 minus cos theta 2. Okay, so the change in the potential energy in this different configuration is P cos theta 1 minus cos theta 2. So if you are given the angle goes from 30 degree to 60 degree, this is your theta 1. Okay, initial angle is theta 1, final angle is theta 2. Okay, so that will give you just substitute the values, and that will give you the change in the potential energy, u at theta 2 minus theta 1, final minus initial. Change is always final minus initial, and this is initial minus final. Okay, so don't confuse change in potential energy. Okay, change is final minus initial. Okay, so now can we make it more elaborate? So in some cases they might only give you one angle. Okay, in that cases we assume that the initial angle is 90 degree, because cos of 90 is 0, and basically the final angle directly defines the potential. So this will be minus P E cos theta. Okay, where theta 1 is taken as 90 degree. So in that case initial potential energy P cos theta 1, okay, theta 1 is 90, then this will become 0, cos 90 is 0, and will be left with minus cos theta 2. Okay, now we are dropping that theta 2 because we are given only one angle. So potential energy, the final expression, if you are concerned with only one angle, if you consider the initial configuration at 90 degree, final expression of the potential energy will be minus P E cos theta. Okay, so at theta 1 is equal to 90 degree, potential energy is 0, right? For this potential energy is 0. Okay, only the theta 2 is survived with the minus sign. Okay, so that's about your potential energy due to dipole. So next we will learn about the relationship between your electrostatic potential and electric field. Okay, now qualitatively discuss the relation between electrostatic potential and electric field. Okay, so we are going to relate a scalar to a vector, which is in itself interesting, right? So first of all, we have already seen this relation. Okay, we'll be just briefly going through this. It's not there in your course to derive this relation in depth. Okay, so they are just stated as some facts. Okay, so here we already know this relation, that your potential is given as minus E dot dr, right? Integral minus E dot dr, minus sign because the potential, the electric field is in the direction of decreasing potential. This is what we discussed in the previous class. Okay, so from here you can actually write the relation for your electric field. E will be given as minus dV by dr, right? So your potential is integral of electric field, so electric field is the derivative of potential. Okay, so that is the relation between them. Now this is however true only for single variable. This is true for true only for single variable. Okay, so your potential must only depend upon r. Okay, in this case dv by dr. Okay, so potential, suppose we can take dv by dx. So if ex can be defined as minus dv by dx. Okay, so your potential should have only x terms in it. So if your potential has x, y, z terms, in that case this relation is not valid. Okay, you have to extend this definition. So in case where your potential is dependent on x, y, z, we use partial differentiation. Okay, this is true for single variable. Okay, so if your potential has only a r term or only a x term, okay, or only a y term, not other variables, okay, only one variable at a time, this holds true. Okay, but for multi variables you will have to find electric field separately. So your basically your potential will only give one component at a time, so you'll have to use partial derivative. Okay, so ex will be minus del v by del x, ey will be minus del v by del y. Okay, I hope you know what this partial derivative means, because we have already discussed it in the previous class, del v by del z. Okay, so we have discussed this in the previous class. You can go check out. We have also discussed a problem on it, so that will make it more clear. So if you are not understanding it as of now, this is partial derivative. This is partial derivative with respect to x. So since your potential has terms x, y, and z, for this derivative we are going to consider x as variable and all others as constants. Okay, here y is variable, all other variables as x and z will be considered as constants. Okay, when you are partially differentiating with respect to y. So similarly, that is the drill, you get it. Okay, so now these are different components of field. The net field finally will be, it is a vector, so it will be given as ex I cap plus ey j cap plus ez k cap. So basically you have to multiply the unit vector. Okay, these are the components, scalar values, so you have to multiply their specific component with them so that you get the vector electric field. Okay, so these are the relation between your electrostatic potential and electric field. Okay, so let us move to the next derivation now. Because potential due to a spherical shell. Spherical shell is basically a hollow sphere. Okay, there is nothing inside. So this is true for a spherical shell, which is a hollow sphere, or this derivation that we are going to do is also true for a solid conducting sphere. Okay, so even if the sphere is a solid, but it should be conducting. Okay, for solid and non-conducting case, suppose the sphere is solid and made up of a non-conducting material, then the case will be different, then the story will be different, which will be the case B. Okay, this is true for a hollow sphere and this is also true for a solid conducting sphere. Okay, so basically conducting, what will happen is that all the charges that you give to that sphere, all the charges will reside only on the surface. So essentially it will act like a hollow sphere only. Okay, so that is how you can remember and connect these two together. Okay, so now we have already found the electric field due to a spherical shell on the point outside the field, on the point outside the sphere. It is given as, it is same as that of your point charge. Okay, so it is basically kq by r square, right? Q over here is small q, and the distance at a point P outside the circle we consider outside the sphere. So this is the electric field outside your spherical shell. Okay, now we already know the relationship between your potential and electric field. You can use this electric field and find the potential outside the sphere. So this will be E dot dr, right? Integral E dot dr, E on the outside dot dr. Okay, they are in the same direction, E and dr. Okay, along that radial direction. So cos 0 basically, and let us substitute the value of the field outside, which is this 1 upon 4 pi epsilon naught q by r square dr, right? So this will come out of the integral sign. Again, you are going to see this will be, the results will be same as that of the point charge. Okay, basically because the results for your electric field are the same as that of the point charge. Okay, so this, as I told you, 1 by r square integral is 1 by r, right? So that minus sign can be removed. So this integral is 1 by r. We can take the limits from 0 to this distance r. So basically we'll end up with this relation kq by r. Okay, so basically same due to that of the point charge. Okay, 1 upon 4 pi epsilon naught q by r square. Now we can also find the field on the surface. Okay, field on the surface, basically your electric field, you have to substitute r value as capital R. Capital R is the radius of the sphere. Okay, so similar changes will be made in your potential. So potential at the surface, you just have to substitute r is equal to r, so which will give us 1 upon 4 pi epsilon naught q by capital R. Okay, or k q by capital R. Okay, this is the maximum value of the field for a hollow spherical shell. Okay, because it's inversely proportional to r, and at this point this is the maximum that it can get. Okay, because inside the sphere, so if you see inside, what is the electric field inside a conductor is 0, right? It is one of the properties of conductor. So electric field inside this spherical shell or solid conducting sphere conducting, so electric field inside is 0. Okay, since basically there are no charge inside, right? All the charges will reside only on the surface. So electric field on the inside is 0, which means dV by dr is 0, E is minus dV by dr, right? So we can say dV by dr is 0, which means potential is constant. Okay, it's not 0, it can be 0. Okay, 0 is also a constant, but in more generally you can say that potential is constant, and since it is constant, it will be the same value as that of the surface, basically due to continuity. Okay, so the potential inside has the same value as that on the surface, which is 1 upon 4 pi epsilon naught q by r, or k q by capital R. Okay, so outside k q by small r, r is the distance from the center, and your on the surface is k q by capital R, r is the radius, and inside it is also the same because there is no change in your potential. Okay, that's why electric field inside is 0, and the potential remains the same as that of the surface, and that is the maximum value. Okay, these two, basically inside and on the surface, is the maximum value of your potential due to a spherical shell. So let's move to one interesting case, which is the solid but not conducting. Okay, so in that case what will happen is basically all the charges that you give to that sphere, they will not move out to the surface. Since it's a non-conducting sphere, they will stay where they are. Okay, so we'll uniformly distribute the charges on a non-conducting sphere, and let's study that case. In this case, this is the conclusion. Let's move to the case B, wherein we'll be discussing potential due to a solid non-conducting sphere. So as I mentioned, the charges are uniformly distributed inside a non-conducting sphere. So here the charges will not move out to the surface since it is non-conducting by very nature. One good news for you is that the potential outside the spherical, this solid non-conducting sphere, and on the surface will have the same relations as that in the previous case. Okay, because basically on outside the sphere and on the surface, you can treat basically the entire charge is at the center, and you can treat it as a point charge and obtain the same relations. Okay, so it is 1 upon 4 pi epsilon naught q by r outside the circle, where r is some distance outside the circle, r greater than r, I can say. And on the surface, you can basically substitute this r is equal to capital R, which is the radius. However, inside the solid conducting sphere, the things are going to change, because in the previous case, if you remember, there was no electric field inside our spherical shell, majorly because there was no charge inside the sphere, right? But in this case, there is charge inside the sphere, so which means there is electric field inside the sphere. Okay, and it is given as if you have followed the previous class, we have derived this relation for electric field inside a solid conducting sphere, 1 upon 4 pi epsilon naught q by r cube into this distance r. This r is some distance inside the sphere, r less than r. Okay, this is greater than r, this r will be less than r inside the sphere. Okay, so similarly we can derive for potential. Now potential we know as dv by dr, we'll use the minus dv by dr. So here we'll obtain the relation for potential. So minus E dot dr I can say, or integral on both the sides, right? This is the relation between your potential and electric field. Here I am using from here because I'll be substituting using limits. Okay, so here we'll choose from surface to point V. Okay, from the surface to point at some distance r. Okay, so here the limits will be from the surface, which is capital R, to small r. Okay, if you are uncomfortable you can flip it over. Okay, from r to surface you can see. Okay, so here dv integration is v, and that will be upper limit minus lower limit, right? So v minus vs. Now this will be you can say electric field inside, or I'll flip it if you are comfortable with that, r by r and E dot dr. Okay, so let us solve it further. So v will be v minus vs, and that will give us electric field. You can substitute 1/4 pi epsilon naught q by r cube, right, into r. Okay, r will remain inside the integration. Okay, r will remain inside the integration. So what have I done here? I have to flip this, right? If I am taking the minus sign inside, I have to flip it. Okay, so r will remain inside, and dr, so small r to capital R, small r to capital R. Okay, so v minus vs, that will give you q upon 4 pi epsilon naught r cube, and integration of r is r square by 2, and you have to take the limits from small r to capital R. Now you can also substitute the value of vs. Okay, we'll take it to the other side and substitute that. So before that, let us substitute this limits. R cube r capital R square by 2 minus small r square by 2 plus, what is this, plus the field at the surface, right? Take this to the other side. So we have 1/4 pi epsilon naught q by r, right? This expression. Now we'll take this whole thing common, right? So we'll have q upon 4 pi epsilon naught r in common. So this r cube which is there will go inside as r square. So r square divided by 2r square. Okay, so I'm giving it inside, r square part I'm giving inside both of this term, and this whole thing is taken common, so plus 1. Okay, so this and this will get cancelled, and we are left with q upon 4 pi epsilon naught r. This is half and this is 1. Right, half and 1, 3 by 2, right? And this is also, okay, there is 2 over here also. Yes, we are doing it correct. So this will be 3 by 2 minus r square by 2r square. Okay, or I can write it in a more simplified format, q upon 4 pi epsilon naught r. Okay, what will we do? We'll multiply this, cross multiply this, so we get 2r square in the denominator, and we get basically we'll get r square, 3r square minus we can say r square, small r square, right? Yeah, so basically I have taken the LCM. Now we can take this r square outside so that it matches with the electric field, basically r cube, q upon 4 pi epsilon naught r cube, and we have some term which is 3 by 2, so it will be 3 by 2 r square minus 1 by 2 r square, right? Or we can write it in a more simple format in the form of decimals. This is 1.5 capital R square minus 0.5 small r square. Okay, and this is the relation for the potential due to a solid non-conducting sphere. Okay, and you can remember it. And one homework question for you, you can please tell me the maximum value of the potential due to a solid non-conducting sphere. For the spherical shell, it was the value on the surface. Here, tell me what will be the case. Okay, so if you have remembered the graph that we discussed in the previous class, you can directly tell me the answer but from here also you can tell. Okay, but do let me know the answers in the comment section. The correct answer will receive a heart. Okay, so it's not that of the surface, it's something else. Let me know in the comment section. Over to the next derivation. Discuss the capacitance part. Here we'll be deriving a relation for spherical capacitance. Okay, and here we'll be finding a relation for energy stored in any capacitor. Okay, so this is very simple. Capacitance is basically defined as Q by V, right? Capacitance is basically the property of a conductor to hold charge. So suppose we have a spherical one, and it holds some charge plus Q, and you can easily find the potential at the surface. Okay, you know the relation now for a spherical shell or even a solid conducting one. So that will be 1 upon 4 pi epsilon naught Q by R, right? This is potential at the surface. Now what you can do is we can bring this in that form. So we can say 4 pi epsilon naught R is Q by V, right? So we'll basically flip it over. So Q by V will be nothing but the capacity of this capacitance. So that is basically 4 pi epsilon naught. Okay, so this is the relation for the capacitance of a spherical conductor or a spherical capacitance. Okay, so this is the relation for it. Okay, it's very simple to derive. Let's come to energy stored in a capacitor. So basically, as I've repeated it 100 times, basically the work done will result to energy. Okay, the potential energy in the capacitance. Okay, how is the work done? The work done is done by storing the charge on the capacitance. Okay, so there is already some charge on the capacitor. You bring some additional charge dq and you make it store on that capacitance. Okay, so your work will be proportional to your dq, and it will be basically v dq. Okay, so since potential is work per unit charge, potential into charge will give you work. Okay, so work is v dq. Okay, for small work dw is v dq. Okay, now we'll integrate this. Now v is given as, if you see this relation, v is given as q by c. Okay, v is given as q by c dq and dw. Now let us integrate it. So 1 by c is constant, capacity of a capacitance is constant. Okay, and here the work done will be basically integration of q with respect to dq will be q square by 2, right? Q square by 2c we can see. Okay, so this is nothing but the energy stored inside your capacitor. This work is nothing but the potential energy of the capacitor. Okay, so half q square by c you can say. Okay, or you can write it in the other forms as well, since your q is equal to q can be replaced by c into v, right? Q is cv, so we can write in place of q cv, so c square v square, 1 cv will cancel, so we'll get cv square. Okay, so you are just using this relation to manipulate. Now we can also substitute for c, so this is in terms of q and c, this is in terms of c and v. Now we can substitute c and we can obtain a relation between q and v. Okay, so c is, so half will remain as it is, and q square by c, c is q by v, so 1 q will cancel and v will go on top, right? 1 q will cancel and v will go on top, so half qa. Let me check that, half qa, yes, correct. Okay, so these are the three relations. You can obtain it in different terms: q square and c square and c and v, and q and v. Okay, so that's about capacitance. Let's move to the next derivation. Let us now discuss capacitance due to a parallel plate capacitor. Here we have a parallel plate capacitor. One plate is charged plus q, other one is minus q. Plate area is a, distance of separation is d. Okay, here the potential between the plates can be easily given as E into d. Okay, of course v is minus integral E dot dr, but here the potential, the field is constant, so you can directly use this relation, v is equal to E times d. Okay, now the electric field due to a single plate that we have discussed, thin sheet, in the previous derivations, which was on the previous chapter, is sigma upon epsilon naught, sigma upon 2 epsilon naught, due to a single plate. Okay, here we have two plates, so sigma upon epsilon naught plus sigma upon 2 epsilon naught. This 2 will give us half and half will give us 1. Okay, so this is the field that we are going to use over here, sigma upon epsilon naught, and d is as it is the distance of separation. Now sigma is nothing but the surface charge density, which is charge per unit area, right? So let us substitute that q, and we get a epsilon naught by d, and here we'll get v. Now capacity can be given in the form of q by v, so let us get this in the form of q by v. So q by v will be a epsilon naught by d, right? Q by v is a epsilon naught by d, q by v. Okay, so this is c, this is a epsilon naught by d, hence proved. Okay, so only a few derivations to go, so let's get to them. So let's come to this derivation on combination of capacitors. Here we have capacitors in series and parallel, so we are going to find the equivalent capacitance in series and in parallel, just like resistors in series and parallel. Okay, but the relations are going to be inverse over here. So let's pay attention over here. Here we will have two capacitors in series. So basically here the voltage is being divided, right? So the voltage is being divided between these two capacitors. So V, the total voltage V will be divided into V1 plus V2. Okay, here the charge on each capacitor is plus Q minus Q plus Q minus Q. Okay, so battery will do this, basically charge the capacitor in the steady state. Here we'll have plus Q, this will induce minus Q over here, this minus Q will bring up plus Q over here, and again minus Q over here. Okay, so in series the charges on both the capacitors remain the same. Okay, that is the idea, and the voltage gets divided. There you'll see that the voltage remains same, but the charges will divide. Okay, so here we know that C is equal to Q by V, so V is equal to Q by C, right? So here this is net voltage, so we can use this circuit, so we can write Q by C equivalent. Now we know that in series the charges are same, Q is same everywhere, so for V1 we have Q by C1. Okay, Q is same, and V2 we have Q by C2. Q will cancel throughout and we'll get equivalent capacitance as this. Okay, it's the reciprocal of the equivalent capacitance is the sum of the reciprocals of the two capacitors in series. Okay, let's come to the parallel case. Here also it is simple. Here you can see that the charges will be separate. Here Q1 let's suppose, and Q2, this will induce minus Q1 on the other plate and minus Q2 on the other plate. Okay, so this is depending upon the capacity of the plates. Whichever plate can have more capacity, more charge basically. Okay, here the voltage remains the same, the charge is distributed, so we can write the net charge Q is Q1 plus Q2. Okay, now we know that Q is equal to C into V, right? Q is equal to C into V. So here we can write for the equivalent circuit, it is C equivalent into V. Okay, and since this is parallel combination, voltage remains the same. So here we will have C1 into V plus C2 into V. So V will cancel throughout and you will get C equivalent is C1 plus C2. So in parallel it is basically the sum. Okay, this is opposite to the resistors if you remember. Okay, so here parallelly the capacitance adds, and in series you have the sum of the reciprocals. Okay, so that's about combination of capacitors. These were all the derivations. As far as your boards is concerned, we have few extra derivations if you want to see them. If you here for the board point of view, you can leave the video here. These were all the derivations from your NCRT and from board point of view, but if you want few more extra, that we those relations that we discussed for current growth and all, those will come up in the next section. Okay, so over to the next section. Last few derivations over here. Here we'll be discussing the charge induced in a dielectric slab which is placed between the plates of the capacitor, and one more which in which we'll be discussing the force on the capacitor plate due to the other plate. Okay, one force exerts a force on the other plate. So what is that force? Okay, so first of all let's come to this one. Let us find the charge induced in the dielectric. So here you can see we have capacitor plates, we have placed a dielectric, it induces charge on the dielectric, the charges on the capacitor will induce charge on the dielectric. We are supposed to find that charge, and you can see due to these charges there is some induced electric field, right, which is opposing the original electric field EO. So the field will be reduced, right? So the net field will be EO minus EI, right? This field, original field minus induced field. Now this net field is actually reduced by some factor K, okay. K is this K is your dielectric constant, so it is reduced, the net field is reduced by K of the original field, okay. So net field will become, is reduced by a factor of K of the original field. So we'll have original field minus induced field. So induced field will be nothing but induced field is EO minus EO by K, okay. We can take EO common and we'll have 1 minus 1 by K. This is induced field, right? So induced field, from here we can find the induced current. We can write sigma in terms of sigma, right? Sigma upon 2 epsilon naught, and 2 epsilon naught will be common everywhere and it can cancel with this. So sigma of I is sigma of O, 1 minus 1 by K, and we can also write it in terms of Q. Sigma is Q by A and A here is common, so we can cancel that. So Q is equal to Q naught, 1 minus 1 by K. Okay, so this is the relation for induced charge on the dielectric placed between the plates of a capacitor. Now this one is also simple. Here the force will be basically Q into E, right? Force, the electrostatic force can be expressed as Q into E, charge times the electric field. The electric field is due to one plate, okay. One plate is exerting force on the other one. The first plate is exerting force on the second one due to its own electric field. So its electric field of single plate is sigma upon 2 epsilon naught. Of two plates is sigma upon epsilon naught, but for a single plate it is sigma upon 2 epsilon naught, okay. Keep that in mind. So sigma E upon 2 epsilon naught is what we get. Now this is the electric field, and here we'll have charge Q, right? Q into E, okay. Q into E. Now your sigma can be expressed as Q by A, and here we'll have the relation. So Q square by 2A epsilon naught is the force on the plate. Yeah, it is correct, okay. So those were the two derivations. Finally we'll do one derivation, which is the current growth and current decay. So with that we'll wrap up with this lecture. The final couple of derivations. First we have the charge growth, and then we'll discuss charge decay. Here we have a RC circuit with some voltage and a switch, okay. So when we close the switch, current will start flowing and the capacitor will steadily grow in charge, okay. So finally the charge that will develop on the capacitor will be the steady state charge. So usually we discuss capacitors in steady state when it is fully charged, okay. There will be no current in the circuit. Initially it will draw some current from the circuit to get charged, right, of course. So this voltage can be represented as, so this voltage will be split up between this capacitive element, which is Q by C, plus IR, right, capacitive element, and the your resistance, right, V is equal to Q by C plus V due to resistor is IR. So we can get it on one side and we can express it as a differential equation. I is equal to dq by dt, so R dq by dt, since we have to find the relation for charge growth, okay, relation in charge. Now we can keep this on one side and take R by R dq by dt to the other side. What can we do next? We'll bring dt and R on one side and dq v minus q by c to the other side, okay. So q variable on one side and t variable on the other. We can integrate this, integrating it from 0 when the switch is not closed, and t when the switch is sometime t after closing the switch, 0, and the initial charge on the capacitor will be 0 when the switch is not closed. The charge on the capacitor is taken as 0 after time t. Let us suppose it assumes some charge q, okay. So dq upon V minus Q by C. Now this integration is T by R and T minus 0, same thing. So here we'll have ln of V minus Q by C, and we'll also have I think in the denominator we'll have minus 1 by C, right, and these have limits 0 to Q. Okay, so T, and this can be taken on top, right, minus C can be taken on top. We'll bring it over here, minus T by RC, and let us substitute the limit. Initially it is same, Q by C, and finally it is 0, so ln of V. Okay, so be careful while substituting the limits. Now you can see that ln of A minus ln of B, so ln of A minus B, so V minus QC by V. Okay, and this is T by RC. Let us take exponential on both sides, so we'll get e raised to minus T by RC is equal to, we can actually split this V, now ln will be 1, split this V, and we'll get Q by CV. Now CV is the total charge, as I've mentioned. Okay, so CV is the total charge that will develop on the capacitor. V is the total voltage, right? Final voltage will be only across the capacitor. The current will be not flowing in the circuit, so V will appear across the capacitor. So total charge will be C times V, which is CV. Okay. Now here Q will be given as 1 minus e to the power is T by RC. This is by Q naught, right? The total charge, final charge. So this is the relation for charge growth. Okay, it's exponential charge growth. You can see that here RC can be also written as some time constant tau. Okay, the graph, if you want to plot, of charge growth versus time, it will be somewhat like this. Okay, finally it will reach a value Q naught. Okay, so that is about charge growth. Let's discuss the final thing, which is charge decay. Now finally consider charge decay. So here we have a CR circuit and we have removed the voltage power source. The capacitor is fully charged at t is equal to 0, but when we close the switch, the current will start flowing and the charge will decay on the capacitor. We are supposed to find the equation for that. Okay, so basically the voltage, we can write it as 0. So Q by C plus IR is 0. I am taking 1 as minus so that they cancel out each other. Net voltage is 0. So now I can be written as dq by dt. So this plus R dq by dt. Okay, this is 0. Now remember that the charge on the capacitor is falling, so the current I is equal to minus dq by dt. Okay, this rate is negative, charge is decreasing. Okay, so dq by dt should be negative. Now let us find this. Minus q by c is R dq by dt. Take q variables on one side and t variables on the other. So we have minus 1 by RC and dt will have on this side, and dq by q. Integrate 0 to t dt by RC minus, and this is initially the charge is fully charged Q naught. Finally after time t it will become q, and dq by q. Here we'll get t by minus t by RC. Integration of dt is t, and t minus 0, again same thing you'll get, and here we'll get ln of q, right, and the limits are q naught to q. Okay, so you can actually okay, let's solve it further. So here we'll have ln of q upper limit minus ln of q naught lower limit. So this will give us ln of q by q naught. Ln of a minus ln of b is ln of a by b, and this is what we get. Take exponential on both the sides, so you'll get e to the power minus t by RC is equal to q by q naught, right? So q is equal to q naught e to the power minus t by RC. Okay, so this is a decay type, exponential decay, you can see that. So here we will have q, here we have t. So the charge decays basically exponentially. It starts from q naught and finally goes to 0. Okay, when this becomes infinity, when t becomes infinity, this term e raised to minus infinity is 0. right? So it will become 0 at infinity. Okay, so similarly in that case, it will become Q naught at infinity. Okay, it actually charges to 99.9%, and that we call it at as steady state. Here from steady state it is going to 0 charge. Okay, so yeah, that's about the final derivation. That's about the class for today. I hope you enjoyed it. If you made it this far in the video, smash that like button and consider subscribing. We'll be doing this one shot 1 hour videos um, for all the derivations from all the chapters. We are also doing the one shot 1 hour series, all the concepts in 1 hour. So if you wish to follow that, that is also available on this channel. So I'll see you soon in the next video. Till then, keep enjoying physics.